Hello everyone, I am Shenghua Wang from the Hong Kong Polytechnic University, and this is a talk of our paper, Complementation in T-Profit Graphs. And this is a joint work with my PhD supervisor, Dr. Yixin. And at first, I would like to show you the results in this paper. And the first result is related to the minimally T-imperfect graphs. And all of these 10 graphs here form a graph class called 3-3 partitionable graph. And this is given by Kawata. And Boone and Steen showed that all of these 10 graphs are minimally T-imperfect. And if we look these 10 graphs closely, we could find that the graph in the second row is just the complement of the graph in the first row. Therefore, every complement of a 3-3 partitionable graph is also minimally T-imperfect. And our results state that graph G and its complement are both minimally T-imperfect graph if and only if the graph is one of these 10 3-3 partitionable graph. And our second result is related to the self-complementary T-perfect graph. And the graph is self-complementary if it is isomorphic to its complement graph. And we can characterize the self-complementary T-perfect graph that are not perfect, and that are all of these 5 graphs here. And our research is related to the T-perfect graphs, and T-perfect graph is come from the stable set polytope of graphs. A stable site is also called an independent site. That is set of vertices in the graph that no two vertices in the site are adjacent in the graph. For example, the red vertices here form an independent site. And we use alpha G to denote the independence number, and that is the cardinality of the largest independent site in the graph. We know that it is NP hard to find the independence number for a given graph, for a given general graph. So what could we do? Maybe we could find some method to find the independent number for some graph in some graph classes. Let's take this P3 as an example. This is a path graph with 3 vertices, and we can find that it has 5 independent sites, empty site, 3 independent sites with cardinality 1, and the independent site with cardinality 2. And for each independent site, we could use a characteristic vector here to represent it. And the stable set polytope of this graph, is just the convex whole of all of the characteristic vector of the independent sites in the graph. So the stable set polytope of P3 here is shown in this figure, and we can see that the stable set polytope of P3 is just the intersection of 5 half spaces, and each half space here could be represented as a linear constraint. Therefore, if we could find the defining linear system of the stable set polytope of the graph, maybe we could find the independence number for the graph by solving this optimization problem by using the linear programming. For every vertex in the graph, we can have this non-activity constraint. This is trivial. And we know that for every edge in the graph, at most one endpoint could exist in an independent site. Therefore, we have this edge constraint. And the edge stable set polytope of the graph is just formed by these 2 kinds of constraints. And back to our previous example, we could find that stable set polytope of P3 could be described by these 2 kinds of constraints. Therefore, the stable set polytope of P3 is equals to the H stable set polytope of P3. And a more general result states that a graph is bipartite if and only if the H stable set of the graph equals to the stable set of polytope of the graph. Therefore, we could find the independence number for bipartite graph by using the linear program. Now, how about non-bipartite graph? And this is an example. That is K3, the complete graph with 3 vertices. And if we consider this vector, that half is coordinate, we can check that this vector it satisfies all the constraints formed by the H-stable set polytope. Therefore, this vector is in the H-stable set polytope, but if we sum up all the coordinates together, we will get a value 3 over 2 that is larger than y, and we know that the complement graph with 3 vertices, the independent number of this graph is 1. Therefore, this vector could not in the stable set polytope of K3. And these two polytopes are not equal. Therefore, we need another constraint for this cancel graph, and we can observe that a clique and an independent set could intersect with at most one vertex. Therefore, for every clique in the graph, we will have this clique constraint. And the clique stable set polytope of the graph is given by the non-negativity and the clique constraints. And based on this clique stable set polytope, we could check that the stable set polytope of K3 is equal to the clique stable set polytope of K3. Therefore, we found the defining linear system for the stable set polytope of K3 just given by these two kinds of constraints. Therefore, we could find the independent number for K3 by using linear programming. And Petberg and Kawata independently showed that a graph is perfect if and only if its stable set polytope is coincident with the clique stable set polytope. Therefore, we could find the defining linear system of the stable set polytope of the perfect graph. And this gives a characterization of perfect graph in the polyhedral point of view. And we could find the independence number for the perfect graph by using linear programming. And we could find a person who is both of these two pictures and who is Bird. Both propose two famous conjectures related to the perfect graphs, and both of them are theorems now. The first one is perfect graph theorem, strong perfect graph theorem, which states that a graph G is perfect if and only if neither G nor its complement contains an induced odd hole. An odd hole is an odd cycle with length larger than 4. And the second one is the weak perfect graph theorem. A graph is perfect if and only if its complement is perfect. And the strong perfect graph theorem is settled by the Thomas, Zimmer, Robson, and Chernovsky in the year 2002. Now we know that the odd cycle and its complement are not perfect. Therefore, for odd cycle, we need to have this odd cycle constraint. Since for odd cycle with length n, there are at most n minus 1 over 2 of vertices in this odd cycle could be an independent set. Therefore, we impose this odd constraint. And together with the vertex, the non-negative constraint, H constraint, all of them form the three constraints forms a polytope called the T-stable set polytope. And Kawata, based on this T-stable set polytope, proposed a class of graph called T-perfect graph. A graph is T-perfect if its stable set polytope could be fully described by these three cancel constraints. Here are some known graph classes that are T-perfect. And among them, I want to mention the almost bipartite graphs because we will use it later. A graph is almost bipartite if it itself is not bipartite. But if we remove any vertex from the graph, the remaining graph will be bipartite. For example, this 5 cycle is almost bipartite, since if we remove any vertex from this 5 cycle, we will get a bipartite graph. Therefore, 5 cycle is T-perfect. But due to the strong perfect graph theorem, we know that it is not perfect. And also by applying the strong perfect graph theorem, we know K4 is perfect. But if we consider this vector, we can check that this vector 1/3 for each coordinate is in the T-stable set polytope of the graph, but not in the stable set polytope of the graph. Therefore, K4 is not T-perfect. Based on these two examples, we know that the class of T-perfect graphs and the class of perfect graphs are incomparable. And here are some operations on the graphs. Based on the definition of the perfect graph, we know perfection is preserved and the vertex deletion. And due to the weak perfect graph theorem, we know perfection also preserved under complementation. And as a key step of proving of the proof of weak perfect graph theorem, laws show that perfect graphs are all closed under doing the substitution. Therefore, perfection is preserved under all of these operations. And for T perfection, we know it is closed, it is preserved under vertex deletion. Since if we remove a vertex V from the graph, the stable set polytope of the remaining graph is just the intersection with the stable set polytope of the original graph with a hyperplane with the corresponding variable xv equals 0. And for the last two operations, we could use K4 as an example, since K4 is T imperfect, but the complement of K4 is T perfect. Therefore, it is not closed under taking complementation. But and K4 could also be obtained from K3 by substituting a vertex by K2. And K3 is T perfect, but K4 not. Therefore, T perfection is not preserved under doing a substitution. And Jaros and Shepard proposed another operation that could preserve T perfection, and that's called T contraction. We do T contraction on vertex V if it's neighbor from an independent set. We contract the closed neighborhood of V into a single vertex, and that is the T contraction. And the operation T minus here is any graph obtained from the original graph by a sequence of T contractions and the vertex deletions. Therefore, we know that T perfection could also preserve under T minus. And a minimally T imperfect graph is just the graphs that are not T perfect, but whose proper T minus are all T perfect. Therefore, any minimally T imperfect graph could not contain another minimally T imperfect graph as a proper T minus. And Loas proved the weak perfect graph theorem, and it states that minimally imperfect graphs are closed under taking complementation. Now, how about minimally T imperfect graphs? Unfortunately, no working conjectures for minimally T imperfect graphs so far, so we don't know what kinds of graphs could be minimally T imperfect. And based on K4, we know that minimally T imperfect graphs are not closed under taking complementation. Therefore, we want to ask, is there any minimally T imperfect graph whose complement also minimally T imperfect? And here are some examples for the minimally T imperfect graphs. The old wells, even more well later. And this graph is the complement of 7 cycle, and the last one is the complement of C10 power of 2. And the last two graphs are called complement of cycle powers. And if we take a close look of these graphs, the first two graphs whose complement graph are almost bipartite. Therefore, the complement of these two graphs are T perfect. I think the next two graphs contains an independent site with cardinality 4. Therefore, the complement of these two graphs will contain a K4. Therefore, not minimally T perfect. And the complement of this graph is just the 7 cycle. 7 cycle is T perfect. Now we're left with the last graph. And the last graph is just a member of 3 partitionable graphs. And all of these 10 graphs form a graph class called partitionable graphs. And that is given by Kawata. And Bruin and Steen showed that all of these 10 graphs are minimally T-imperfect. And the graph in the second row is the complement of the graph in the first row. We can check that. Therefore, any partitionable graph whose complement graph is also minimally T-imperfect. Now we want to ask, is there any other minimally T-imperfect graph whose complement also minimally T-imperfect? Our one theorem gives a negative answer to that question, which is that both the graph and its complement are minimally T-imperfect if and only if the graph is a partitionable graph. And the backward direction is quite trivial. It's based on the result of Bruin and Steen. And the natural part is the forward direction. We assume now both graph and its complement are minimally T-imperfect. Therefore, the graph cannot contain a k-fold or its complement. And since the complement of 7 cycle is minimally T-imperfect, and any odd cycle with length larger than 9 will contain a k-fold. Therefore, we could conclude that G cannot contain a odd cycle or its complement with length larger than 7. And G should contain a 5 cycle. Otherwise, we will show that G will be T-perfect. This is because if G contains no 5 cycle, and together with the atom 2, we could show that G is perfect, since it contains no odd hole and odd anti-hole. Therefore, the stable set polytope of the graph could be described by the non-negativity and clique constraint. Since the graph G cannot contain a k-fold by atom 1, therefore the clique stable set polytope whose clique constraint will degenerate to the H and the odd cycle constraint. Therefore, the stable set polytope is coincident with the T-stable set polytope of the graph. Therefore, J is T-perfect, a contradiction. Now we know G should contain a 5 cycle. Now fix the 5 cycle and consider the adjacency of the 5 cycle with a vertex outside the graph or outside the 5 cycle. And we consider the graph induced by the 5 cycle with a vertex outside it. If this vertex have 5 neighbors on the cycle, then it will form a farewell. Since farewell is minimally T-imperfect, that's a contradiction. And if the vertex have 4 neighbors on the 5 cycle or have 3 consecutive neighbors on the 5 cycle, then we could do T contraction and this vertex and this vertex. That will give us a k-fold T manner in the graph. Therefore, for these 3 situations, we made a contradiction, and we will make the same contradiction in the complement of G if this vertex have no neighbors on the 5 cycle, or have exactly 1 neighbors, or have 2 neighbors that are not consecutive on the 5 cycle. Now we left this case. This vertex should connect to 2 consecutive vertices on the 5 cycle. And if this vertex have 3 vertices on 3 neighbors on the 5 cycle, then this vertex neighbor on the 5 cycle should not be consecutive. Now here we use the green line to represent the H may or may not exist in the graph. And we show that every pair of consecutive vertices on the 5 cycle has at most 1 common neighbor. Otherwise, if it have more than 2 common neighbors, we can see for these 2 graphs as an example, it will contain a k-fold or a k-fold here, or contains a independent set with cardinality fold, and that contradicts with our atom 1. Now we can conclude that the graph G has at most 10 vertices. Now the desired graph G should in one of these 10 patterns, 8 patterns. And for each pattern here, we use the black edge to represent the edge that we are sure we know they are in the graph, and the green edge here is the potential edge. That edge may or may not be in the graph, and other edges are not allowed in the graph. And if we assume some potential edges existence in the graph, then we will obtain a graph in the corresponding pattern. For example, for the pattern B, it have one potential edge. If this edge exists or not exists in the graph, we assume we will have two graphs in this pattern. And for pattern A, B, and C, we show that all graphs in these three patterns are almost bipartite graph. That all of them are T-perfect. And we show that pattern D, graphs in pattern D and graphs in pattern F, whose complement will in pattern C and pattern E. Now it suffices for us to consider the graph in pattern E, pattern G, and pattern H. And let H be a graph in these three patterns. And if H is not a Cauchy partitionable graph, then H or its complement is not minimally T-imperfect. Therefore, if we could show this, then that will conclude our proof. Now we show some approaches we use to show H or its complement is not minimally T-imperfect. By assuming some potential edges exist in the graph, we may obtain a graph H or its complement contains a K4 or the complement of K4 here. And Kawata showed that a minimally T-imperfect graph could not contain a clique separator. Therefore, if we could show that H or its complement contains a clique separator, then they will be minimally T-imperfect. They will not be minimally T-imperfect. And by assuming some potential edges exist in the graph, these new potential edges may form a new file cycle in the graph. And with a vertex outside of this new file cycle, that may lead the graph contains a K4 or W file T matter and make a contradiction. The last tool we use is to show that H or its complement is T-perfect. We use two methods to show that. One of that is we know that Cauchy partitionable graphs are shown to be minimally T-imperfect, and we could just show H or the complement of H is an induced subgraph of it. The second one is by using the following lemma. If the graph if there exists a clique in the graph such that we remove any vertex in this clique, the remaining graph is T-perfect. Then the original graph will be T-perfect. And all of these are our approaches to show the obtained graph H or its complement in the corresponding pattern are not minimally T-imperfect. The rest of the proof is just the analysis of the patterns, analysis of these graphs H. If you are interested in it, you can get the detail in our paper. And the next result is related to the self-complementary T-perfect graphs. And at the beginning, I will show you that I will categorize the self-complementary T-perfect graphs that are not perfect, and that are all of these 5 graphs. And now the open question is that how many self-complementary graphs that are both perfect and T-perfect? Since by using the 4-pass addition, we know that we can construct an infinite number of self-complementary perfect graphs, but almost all of them contain K4, therefore they are not T-perfect. And we know by the Ramsey theorem, a graph with more than 18 vertices, it will contain a clique or an independent set with cardinality 4. Therefore, it suffices to us to consider graphs has at most 17 vertices. And we believe that the number of these graphs will be small. And that's all. Thank you for your attention.